that mesh over there, so it's a little more. Okay, so I would first like to thank the organizers for this wonderful conference. While you guys were on your excursion yesterday, I was doing my own archaeology. I found the real gem. This doesn't work. So you can see that this is another data point for time progression. It's in the last millennium. Okay, so happy birthday, Elsa. I will tell you today about work that we're doing in my lab here in this building. These two guys are part of it. They're sitting in the back here. And so I'll just start. So the work started when I attended a conference and saw Matsuda give a talk in which he showed this plot of the penetration depth in one of the Pnictides as the same Pnictide that James spoke about before, as a function of doping. And you can see this, there are actually two striking features in this plot. One of them is that when you reach really low dopings, when there is no superconductivity, it looks like the penetration depth has a finite value. That's really strange. The other one is this really sharp peak, which is even stranger, because it tells you that in some sense, this superconductor, so this peak occurs at optimal doping. So in some sense, at the very doping in which the onset of superconductivity is at the highest temperature, the superconductor is the worst superconductor. Lambda penetration depth is large, and therefore it's least able to expel magnetic. Okay, so it's really weird, and usually one doesn't see a tendency. So that was the impetus for the work. This is my outline. I'll tell you a little bit about the Pnictides and examples. Then I'll introduce the technique that we use, which is magnetic spectroscopy. I'll explain how we measure, and then some of the stuff that we discussed. Maybe at the end I'll show you a slide on what we're doing now, which is how we're working now on experiments. Okay, so I'm following James Analytis' talk, so I'm not going to dwell too much on this. This is a typical phase diagram for the Pnictides. This is not the compound we'll talk about today, but the phase diagram looks very similar. You have a superconducting dome. At low doping, you have a coexistence region with a spin density, with a nematic phase. This nematic phase has a spin density wave, and the crystal structure is wrong. Now, you can induce superconductivity in this compound either by doping by electrons or holes, orbit pressure, or by isovalent substitution, which is what you do in the phosphor dope compound. Here's a generalized phase diagram. You can see that electron dope, phase diagram for electron dope looks very similar to the phase diagram for holes, hole dope, and for the isovalent substitution. That's I'll note that we're actually measuring a standard sample. As you saw in James' talk, there are a lot of weird features that happen in this compound around optimal doping. There are these strange powers in resistivity. There's also there seems to be an enhanced mass as you approach optimal doping. So this one here is optimal doping. Doping level. Another properties as well. In particular, the peak and the penetration depth. And I'd like you to note that for a lot of these properties, a lot of these quantities are measured above TC. So one of the things that's special about the penetration depth is that something weird is happening when you're in the superconducting phase. You're not measuring above TC, you have to measure below TC. And I should say that there's an argument on how to obtain such a peak. It seems to be pointing, it might be pointing to a quantum critical point, but it's not at all obvious how a quantum critical point would give you a peak in the penetration depth. There's recent work that says that what's going on here is actually a first order phase transition where you have a microemulsion between the two phases, and And so you have superconductivity being suppressed in the boundary region between these two phases, and as a result, the penetration depth goes up. In this picture, lambda increases because the superfluid density decreases. In other work, it's the effective mass that's increasing and causing penetration depth to go up. Okay. So we wanted to repeat this measurement for several reasons. One is that the absolute value of the penetration depth is a tricky quantity to measure. It's very useful to try to get the same tricky quantity from a completely different way. So that's in any case. In addition, our measurement is spatially resolved, and so we don't average over the whole sample. We can tell how each part of the sample behaves. We average on regions that are micron. So, for example, if there are inhomogeneities, we can maybe see them, give limits on them if they're absent. And in addition, our probe is magnetic, so we can look for magnetic phases while we're doing this kind of measurement. Okay, so here are the samples that we measured. They're grown in the Matsuda group in Kyoto. And they're grown by standard techniques. We clean each sample before cooling it down. The samples will clean it. Okay, so how do we measure? We use a magnetic force microscopy. Essentially, we have a sharp magnetic tip, which we can bring close to the surface of the sample, where it's going to interact with the superconductor sample. So this means that we get local information. It also means that we don't need to do a lot of sample fabrication. We can just bring the tip to the sample. That's very useful. That's some of the downsides of measuring penetration depth with other techniques, that you need to deposit all kinds of material in the sample. And also, if we can move away from cracks, edges, obvious things that are going to distort our measurement, and we can also get, as I said, spatially resolved information. In addition, we can also go to finite magnetic field, where we're going to trap vortices, and then we can either get information from where they sit in the sample, or by dragging them, see how they interact with defects in the. So the way we measure is, so here's this sharp magnetic tip that we bring close to the surface of the sample. This is an example of a vortex. The tip interacts with this local magnetic field. As a result of that, there's a force that acts on it, and that bends the cantilever. And we actually measure the resonant frequency of this cantilever. This gives us information about the local gradient. So the images I'll show you, or the traces I'll show you, are measurements of this frequency shift, which is proportional to the gradient of the force acting on the tip. So here's an example. Here's a tip. This is an actual tip. This is a cartoon of a sample. And I'll show you what happens when you're below TC and you bring the tip to the sample and measure the frequency shift, which is gradient force. And what you see is that there's a sharp upturn. This, if you think about it and work through the science, is Meissner repulsion of the tip of the sample. Okay, so if you have an attractive force, it would curve the other way. So that's a sign for us that we're over a superconductor. So you can repeat this measurement as a function of temperature, and at some point this signal disappears, and you have an estimate for TC. And this TC is from a very small area. Okay, so it's on the scale of a few microns. So how do we use this to measure the penetration depth? So when your tip, the reason there's Meissner repulsion is that there are screening currents screening the field from the tip in the sample, and they're fully worked out. You can get expressions for the kind of repulsion that you'll get. And you take one of these curves and you fit it, and you get an estimate for the penetration depth. And again, the information is from a very small area. So here's a bunch of measurements. These are almost all the measurements. I'll add the very low doping later. You can see both TC, this is this axis, and the penetration depth as a function of doping on the same plot. And what you can see is that, and it's important to note that at each doping, well, we measure TC and the penetration depth at each location. Okay, so each penetration depth depth comes with the local TC. That's something important. First thing that you can see is that there is indeed a peak in optimal doping. It might not look as impressive as the peak in the original pseudo work. That's because we didn't square it. If you square it, it's less impressive. What is also clear here is that both TC and the penetration depth are very uniform. So you see multiple points here, and that's because for each sample we measured at a few points. And some dopings we had several samples. The results are very, very consistent. You move to a different place, you get the same result. So that says that in some sense we don't see very big inhomogeneity. You can now, in a plot like this, what I plotted here is a function of doping. You never really know what the doping is because you never know that the atoms, substitution atoms, are in the correct locations. So it's useful to plot things where you take that out of the equation. So here's a plot of TC as a function of 1 over penetration depth squared. It's akin to the Umura plot. And you can see that all of our points fall on this on one line. You cannot tell from this plot which side of the transition you are. This is a refinement of what was seen in the sample wide measurement, where there seem to be 2 branches. I can only say that this is almost perpendicular to what you would get in a Umura relation. Maybe it's a hint for the theorists for what's going on here. I didn't fit any powers here because we don't have that many points. So what happens with the very underdoped samples, the very underdoped samples, it turns out that they're much less uniform. And that's actually an advantage. If you have a really bad sample, then if you move to a different location of the same sample, you get a measurement from a different doping. It's very convenient. So here are those points added to the plot that I showed you before. You can see that we have 3 different TCs on this plot, and 4 different, well, I guess there are 4, and 2 of them overlap. And then there are a bunch of values of lambda. The measurement is reproducible. If you repeat the measurement over and over again, this is not noise. This is just reflecting the fact that the doping is different in the area where we're doing the measurement. And what you can see now is that we can see the fate. Sorry, let's put it on this plot. You can see that these points behave very differently from the points I showed you before. They're kind of closer to what you would expect in a Umura relation. I wouldn't make too much of it, but they sit here. You can see it's kind of more than you picture. The higher the TC, the smaller the penetration depth. And you can see what is the fate of the penetration depth as you reach the end of the dome. It doesn't stay finite, it actually shoots up, and this is what you expect because you're losing superfluid density to a competing phase, so your density goes down and the penetration depth goes up. So this is in fact something that...
Do you have a way to estimate what is the variation in doping level?
We know that the doping level, so the question was, we can estimate the variations in doping. If you do EDS, so the other dopings, the higher dopings, the variation is less than 1% from what you would expect. This is when you analyze just the chemical analysis. I don't know where the atoms are. In underdoped samples, the variation is double. It's not much more than double, but it's really hard. There are tricks that you can do. They're difficult. They've been done in YPCO. Growers work really hard on it. It's really hard to tell where the atoms actually go. The next thing that we did is cool and finite magnetic field. This is something that we do to locate where defects are. So interesting, it gives you an indication of the disorder level in your sample. The way we do this kind of measurement is we park the tip at a constant distance from the surface, and then we raster it, keeping the distance constant, so we're getting a cut. And vortices show up as these round blobs. They kind of look like the signal of magnetic monopole, which is how the electrodynamics works out. So in all of the samples, except the underdoped samples, you can see very organized vortex arrays. This immediately tells you that the samples are pretty high quality. What's important for where the vortices are sitting is the vortex-vortex interactions, and not the local defect landscape. So this gives you a handle on the quality of the samples. If you go to very underdoped sample, where you expect to see very big vortices, you indeed see very big vortices, everything is very smeared because the penetration depth is large, but you can also see that you see these sharp features, and these tell us that vortices are moving. So despite the fact that vortices are really big, so the force we're applying with the tip is very small, vortices are very weakly thin in very underdoped samples. It's kind of counterintuitive. Usually when penetration depth is big, you can't apply very much force, and then you can't move things around too much. And this might point to two kinds of explanations. Either there's lots of disorder, either because of the material quality or because of something intrinsic, and then it's a disorder that gives homogeneities on a scale that we can't resolve. The vortices can resolve the scale because what determines where a vortex is sitting in your superconductor is the coherence length, which is on the order of a few nanometers, way below our resolution. It's also possible that thinning is weaker because the coherence length is growing as you approach the edge of the dome, because you're losing, you're suppressing pairing in the gap. The big surprise for us came from mildly underdoped, slightly underdoped samples. When we cooled the finite magnetic field, we saw these lines of vortices, and these lines of vortices are roughly 45 degrees to the crystal axis. This is the direction of twin bond. So these samples are orthorhombic. They start out at high temperature in the trigonal phase. As you cool down, you get nucleation of orthorhombic domains, and where they meet, you get a twin boundary, and it's parallel to the direction of these lines of vortices. And our initial guess was that the vortices sit on twin bonds. This is what you see in other superconductors. So this is also work in my lab. This is these are vortices in a YBCO sample, and this sample is microscopic, but it had two twin boundaries, and this is one of them, and it sucks up all of the vortices in the sample. This is also the case in this iron-based superconductor ferroselenium. Here's an STM measurement of the gap, and you see that the gap is suppressed on twin boundaries, and indeed they act as traps for vortices. So you can see that they extracted allocations of vortices, and they sit on twin boundaries. And this was our guess for our sample as well. And so here's an image at high magnetic field, which is above 130 Gauss, and you can see a lot of vortices, and they coalesce in these lines. Okay, twin boundaries trap vortices. This is also the case in low magnetic field. But if you go to very low magnetic field, you see that this is not the case. Okay, so here I'm scanning the tips at a constant height above the surface, and you can see that the vortices seem to avoid these bright lines. And if you look at my color scale, you'll realize that these bright lines are places where the tip is repelled more from the sample than the darker lines. That would mean that maybe, so penetration depth could be, superfluid density could be higher on these lines. But that's an interpretation. The Meissner repulsion of the tip is stronger on these lines that seem to repel vortices. If you go to even lower magnetic field, you see that they survive. They're still there. So the superconductivity is modulated by these lines that are parallel to twin boundaries. If you go to intermediate fields, then you see that these lines, these stripes, have an inner structure because they can trap vortices. Okay, so if you force vortices, if there's enough pressure for vortices to overcome whatever this is, then they find a place to sit. They actually look a little weird. I don't know if this, if you can see that they're brighter than the other vortices. I don't know if this is, we're still working. So I don't know if this is something important or something completely different. How am I doing with time? Okay, so we can also manipulate. I'm not going to dwell on this too much, but if we bring the tip closer to the sample, we enhance the forces between the tip and the vortices, and we can drag them. We attempted to drag vortices across these stripes and failed. So they're barriers for vortices avoid them when they nucleate or enter the sample, and they also act as barriers for vortices. This is not a completely unique effect. Similar phenomenology is seen vortices, and it's hard to drag vortices across them. So other than, there are a few notable differences from our measurement. First of all, at the time, I was at Stanford, we were measuring similar samples, and we didn't see, by NFM, we didn't see anything that looked remotely. So, and this kind of cast doubt on, maybe this is some kind of weird measurement, but here we found another material where this happens, so no doubts needed. The other is that the scale is completely different. You can see that the stripes are much narrower and smaller in our case. I should note that our resolution is much, much better than the squid. The squid measurements are resolution limited to the size of the probe, which is a few microns. Our measurements are limited to the penetration depth. So whatever the resolution is set by the superconductor itself. The interaction between the tip and the sample, the best resolution you can get is the penetration depth, and that's where we're saturated with resolution. So there's actually a phenomenological model that was invented to explain this data, and we implemented it for our data. So you can look at the papers to look at all of the calculations. And here's some data. These are these blue crosses. And here's a fit to the model where the only thing we play with is the strength of superconductivity on two-dimensional sheets and where these sheets are. And for our data, to explain our data, you have to have the sheets coming in pairs. Okay, so it seems like that the bright stripes that we see are narrow domains. In fact, if you scan the same region over and over again, and here we're doing it as a function of temperature, you see that there's one stripe here, this stripe, that kind of retracts towards the bottom of the scan area. Here it's almost fully retracted. This is despite the fact that we're measuring well below the threshold. So whatever is pinning these domains to their position is pinning them very weakly. You can also see that this effect disappears as you warm your sample towards TC. So you can see that the amplitude of the stripes disappears as you approach TC. This is also different from what was seen before in the electron doped pnictide contrast improvement. There are, and we don't know the origin of these structures. So the origin for the reason for superconductivity to be enhanced on these sheets on twin boundaries, there could be mundane reasons. I will note though that we see this now in two pnictides, one electron dope, one isovalently doped. This other compound that I showed you before, the ferrum selenium, in that material, vortices are trapped by twin boundaries. One of the main differences between that material and our material is that that material doesn't have magnetic fluctuation. So it's possible that by suppressing when you suppress magnetic fluctuations, twin boundaries act as traps, and if we don't, then they repel. So this is my summary slide, but I would like to, so I'll summarize and then I'll do a promo. So we found the peak in the penetration depth at optimal doping. This is both in bulk measurements that was done before us, and we did local measurements. So this gives you an upper bound on texture of a few microns. TC's dependence on the penetration depth is the same on both sides of the peak and the penetration depth. We also see an enhancement of the penetration depth as you go towards the edge of the superconducting dome. And I just told you about stripes in mildly underdoped materials. And my promo is, we just started work on fermions and thin films, and I don't have time to talk about it. We really just started it, but I'll leave you with this slide. This slide is very heavy. So we did these measurements here, and this scan was done by our collaborators at NTU. And what we're trying to do is correlate between the Hall effect. So here's a measurement of rho xy after you subtracted known effects from it. And we're correlated the texture that we see with features in this plot. And I'll leave this up for you to look at. This is these are films of so these are stacks of platinum and cobalt.
So I have a comment and a question. So the comment is actually when I first met Asa, I came to him with Venus data on the cobalt domes, and he pointed out to me that along the twin boundaries you have, in some sense, a restored tetragonal symmetry, right? And it turns out that maybe that's what favors superconductivity. A year later, there was some data from the Canfield group which showed that as you cool down the sample on the just underdoped side of the phase diagram, that at low enough temperatures, below superconductivity, you actually go from orthorhombic back to tetragonal. So the lower in temperature you go, and deeper into the superconducting state, you actually prefer a tetragonal state. And from then on, it went into like more of this pneumatic business, and it kind of led to those kind of conversations. Okay, my question is, your data on the penetration depth, it seems very clear that there's a big peak on the underdoped side. Does that mean that Mitsuda's original interpretation of the divergence of the penetration depth at centrifugal doping is wrong?
No.
Because it doesn't diverge, right?
I think maybe they didn't show this. Maybe, well, they're averaging over a whole sample. Maybe it gets washed out. Maybe they didn't have that token. I don't know. I mean, it doesn't.
But I mean, you see more of a divergence for underdoped than you do for the
sure. I mean, actually, what I saw is, yes, that's really striking. You can't have that. The peak at optimal doping is there, for sure. We measured it. Actually, my student was showing the group it's not there. And but it's there.
So let me ask that question again. On the extreme underdoping side, are you in disagreement with Matsuda's data on Matsuda's sample?
So it's different samples that they sent us. And yes. But it has to diverge. I mean,
no, but it's has to or not, I mean, I'm just asking. That
and we have to look carefully at exactly what dopings they were using. I have to look at the plots. It diverges very sharply. Also, the sample is very non-uniform. So you could see a very wide variation in the penetration depth.
But that wouldn't give you a fine, I mean, that wouldn't explain the difference between a finite answer and a apparent
yes, but yes.
answer.
So, I mean, yes, the answer is yes. But he's on the paper.
So again, for the underdog region, so you're doing one measurement and you're tracking two parameters. It's critical temperature and the penetration depth.
It's one kind of measurement. What you do is you scan, you find an area that you like that's away from 46 degrees, you don't want to use data. Then you bring the tip to the surface and measure. And you do this several times, and then you increment the temperature. Then you increase the temperature and repeat the measurement. So the low temperature touchdowns give you the estimate for the low temperature penetration depth. And then when you stop seeing, Meissner effect, that's your estimate for TC. So it's many measures. But there are fitting parameters. But we try to eliminate them. So we're thinking about ways to get around having to fit. We've minimized the number of fitting parameters. There's still a fit here. It's touchy, it's tricky, and otherwise.
Asa, can you display these pictures here?
Not yet. No, so what you see is, what happens here is that you take this thing, so there's a recent explosion in fermion physics. People now know how to make samples with fermions at room temperature. So, and these are these thin film samples. We're doing actually low temperature measurements because there's an interesting trace diagram to explore. What you can see here is you take a sample, you saturate it with a very negative field, and then you increase the field. And it's a magnet, so you're going to get domains splitting the other way. And so this is what you see here. So this is actually 0. If you look at the scale here, it's very, very small. So the scale here is 0.04 hertz. This is what you see. So this is what you would get if you had a uniform magnetic film. If you have domains, as soon as you get domains, you get much bigger signal. So here the signal is, I don't know, 5, 6, it's a lot. It's hundreds, more than 100 times bigger. And you can see these domains. And if you look closely, you see these round areas. So those are okay. Where are you? We don't know, but they might be discriminated. And if you increase the field more, then these domains kind of grow, and then you get to you start getting this really fine texture, and you might get fermions of the opposite variety, and then you complete this loop. Actually, the most promising set of measurements that we did is a slightly different sample, where we could see domains like this, and we deleted them, and what was left behind were circles that would move around. They might be fermions, but we're still working on this.
Before Nathaniel makes an announcement, let us thank all the speakers of this session.